In the first linear algebra video in this chapter, I talked about addition, subtraction, transposes, and multiplication of vectors and matrices. I skipped division, partly because division-like operations are really important, so that's all I want to cover in this video. The material in this video is really useful for engineers because these methods can be used to determine the solution to a set of linear equations. Large portions of an engineer's time, at least in my experience, are spent writing and solving the systems of equations governing engineering systems. Before I discuss linear algebra's version of division, which includes a process called matrix inversion, I want to talk about dividing scalar values. Keeping in mind how to divide scalars should give you an idea of what's happening when we invert matrices later. Division can be done in terms of multiplication by an inverse. So I can divide a number a by a number b by multiplying a by 1 over b, or the inverse of b. The product of a number and its inverse is defined as being 1. An inverse can also be expressed as the number raised to the negative first power. One exception to this is the number 0, since the inverse of 0 is not defined. I'll treat matrix division as being analogous to division by a scalar. When I'm performing division-like processes in linear algebra, I'm actually multiplying by a matrix inverse. Since a scalar inverse is defined in terms of the number 1, we need a matrix version of the number 1, which is called an identity matrix. An identity matrix is defined as having 1s on its main diagonal and 0s everywhere else. By definition, if you multiply a number by 1, you get the original number back. In linear algebra, an identity matrix can play the same role as the number 1, since when you multiply a matrix by the identity matrix, you get the original matrix back. To show how this works, I'll look at multiplication of an arbitrary 3 by 3 matrix by an identity matrix. So, for example, the first row times the first column is this term, so a11 times 1, 0 times a12, plus 0 times a13 recovers that term back. a32 is generated by multiplying the third row by the second column. a31 is multiplied by 0, a33 is multiplied by 0, so a32 goes in that position. And the final matrix is the same as the original matrix. As we've seen, matrix multiplication in general is not commutative. Multiplication by an identity matrix is. It doesn't matter whether you multiply I times A or A times I. If A is a square matrix, you'll get your original matrix back. Now we can define the inverse of a matrix. Similarly to scalars, multiplication of a matrix by its inverse results in the identity matrix. It doesn't matter whether you post-multiply the matrix by its inverse or pre-multiply the matrix by its inverse. This is the definition of what a matrix inverse is, but it doesn't really help you know how to determine the inverse of a matrix yourself. Luckily, for this class, we'll let Matlab calculate the matrix inverses and leave it to a later class to give you the background on how to calculate an inverse yourself. Also, as with scalars, the inverse isn't defined for all matrices. The condition for a matrix to be invertible is that the matrix is full rank. This means that the rows of the matrix are linearly independent, which is a way of saying that every row of the matrix has to contain separate information from all the other rows. Now let's talk about some Matlab commands related to these concepts. The Matlab command to create an identity matrix is EYE. If you send the command a single argument, n, it will create an n by n identity matrix. There are a variety of approaches in Matlab to invert an array. The first is the INV command. Just send the command the matrix you want to invert as an argument, and it'll return the inverse. You can also create an inverse by raising the matrix to the negative first power. Using the matrix division operator to divide the identity matrix by A also creates an inverse. You can use either the forward or the backward slash operators for this. Notice that when doing exponentiation or division, we're using the undotted versions of the operators. Undotted operators perform matrix operations according to the rules of linear algebra. First, I'll create a 3 by 3 identity matrix named ident. So, ident equals EYE of 3. I'll also create a 3 by 3 matrix A, which equals 1, 2, 1, semicolon, 2, 3, 3, semicolon, 1, 3, 1. If I pre-multiply A by ident using Matlab's matrix multiplication operator, I get A back. Pre-multiplication just means that the identity matrix appears before the A matrix in the multiplication operation. Since matrix multiplication isn't commutative, we generally need to specify the order of the operands. In multiplication by an identity matrix, I should get the same result if I post-multiply A by the identity matrix, so that the matrix A appears first in the operation. And we do get the same result. Now I'll invert the A matrix using the inv command. So I'll create a variable A inv is equal to inv of A. To check to make sure that A inv is an actual inverse, I'll matrix multiply A times A inv. That does look like an identity matrix, but let's look a little closer. I'll change the format by typing format long E and then redo the calculation. We are seeing some round-off errors associated with inverting the matrix. In this case, those small errors probably aren't a problem, but do remember that they exist. I can also invert a matrix by raising it to the negative first power. So I'll type A caret negative 1. That gives me the same answer as before. Dividing the identity matrix by A using the / operator by typing EYE of 3 / A also gives the same answer, as does using the / operator and typing A / EYE of 3. Recall that in both cases the operand on what I think of as the uphill side of the operator is the numerator. Finally, let's take a look at another matrix B equals 1, 2, 2, semicolon, 2, 3, 5, semicolon, 1, 3, 1. I'll try to invert this matrix by typing inv of B. In this case, I get an error message. Matlab claims that the matrix is singular to working precision. Singular matrices can't be inverted since that would involve something similar to dividing by 0. The reason that Matlab specifies that it's singular to working precision is because round-off errors make Matlab sort of unsure as to what 0 actually is. Remember that numbers less than EPS can't be reliably used in mathematical operations. The matrix B is singular because not all the rows in the matrix are independent. I can get the elements in the third row by multiplying the first row by 3 and then subtracting the second row from that result. So the first two rows taken together can be used to create the third row. That means this matrix is not full rank. The rank of a matrix is the number of independent rows, and for a matrix to be full rank, its rank has to be the same as the number of rows. To check the rank of the matrix B, I can type rank of B. The rank is 2, and the matrix has 3 rows, so the matrix is not full rank and it can't be inverted. Now I'll check the rank of the previous matrix A. The rank of A is 3, and since that matrix had 3 rows, it is full rank, and Matlab had no trouble inverting it. In the next video, we'll put matrices to work solving engineering problems. I'll also try to provide a little insight into some important properties of matrices without providing detailed mathematical discussions of those properties.